if V is an abstract vector space, then those four properties hold. These four. Now remember that vector addition can be strangely defined. Vectors and scalar multiplication can equally be strangely defined. So, for example, for A, we can't just say 0 times vector u, which is 0 times u1, u2 up to u sub n, is equal to 0 times each of those, which is 0, which is the 0 vector. Nonsense. Okay? Scalar multiplication can be strangely defined. All we're allowed to use are the definition of a vector space. Now, we know that 0 is equal to 0 plus 0. Nobody's going to deny that, because these are just real numbers. That addition is normal. That addition is normal. Okay? Now, 0 times u is equal to any way of writing a scalar u times u. Now, one of the properties of vectors is that the scalars get to distribute if you have a sum, or I guess I should say the vector distributes. You get 0 times vector u plus another 0 times vector u. Now, v is a vector, and that scalar times u is a vector. That vector has an inverse. And when you add the inverse, you get back the 0 vector. And when you add the inverse on the other side, you add negative, well, that gives you 0 plus 0 times u. But this is regular addition. So we have the 0 vector is equal to 0 times the vector u. But this is exactly what I wanted to show. So that one is done. The proof for A. Now the proof for B. Okay, so we know that the 0 vector plus the 0 vector is equal to the 0 vector. Those two are equal. Well, I want to multiply both of them by c. Okay, we can distribute the c. So we get c, so this is proof for B. You get c times the 0 vector plus c times the 0 vector is equal to c times the 0 vector. But these are all vectors in vector space V. So I can add on the inverse on both sides. I can add on the inverse. This becomes 0 plus c0, which is just c0. The right-hand side is the 0 vector. So any scalar times the 0 vector gives me back the 0 vector. Okay. So let us look at the proof for C. In my opinion, this is a bit more complicated. Okay, so if C is 0, then by part A, C times U is 0. Okay, so suppose C is not 0. We talked about what happens when C is 0, and now we're going to talk about when C is not 0. want to get that u equals 0. Okay. So we know that u is equal to 1 times u. That's one of the defining properties of a vector space. But now if c is not 0, it can equal to 1 over c times c. That is, 1 can equal that times u. But this is 1 over c times cu. And we are assuming that that equals to 0. So this is a non-zero number times the 0 vector, which equals to the 0 vector. And this is by part A. Well, let me think. Part B. This is by part B. C is non-zero. It didn't say it had to be non-zero. It says for any scalar. In particular, when c is non-zero, you multiply it by the 0 vector and you get back the 0 vector. So here's a non-zero number, or any number. Well, it has to be defined. This is defined. And you multiply by the 0 vector, you get back the 0 vector. So C is proven. Part D. Negative 1 times u is negative u. Now, how I might do that is as follows. We know that 1 minus 1 is 0. 1 plus negative 1 is 0. Therefore, when I multiply it by u, I get 0 times u, which is 0. 0 vector. Now let's distribute. We get 1 times u plus negative 1 times u. And this is still equal to the 0 vector. But we know that 1 times u is u. So u plus negative 1u is equal to the 0 vector. Now, on both sides, I'm going to add the inverse of u. And add negative u to both sides. On the left side, I have the 0 vector plus negative 1u, which is just negative 1u. On the right hand side, I have 0 vector plus negative u, which is just negative u. Okay, so I've proven that negative 1 times u, which is exactly what I have, equals to negative u. I mean, the one thing I can say is I didn't need these parentheses. Equals to negative u. Exactly what I wanted. That completes this video. You need to know how to prove these things. You have to think in an abstract way. And that's exactly what this channel is for, is to get you to start thinking mathematically. You have to open up your mind, think more clearly. It's exactly what I learned as a student at the City University of New York. I learned how to think mathematically. And at this point, I like to say thanks for watching, and watch and learn. See you in the next video. Bye.